What I'm going to talk about next is mostly about mixing processes when two streams come together, and that region of the river is called the river confluence. And in particular, I'm going to talk about the case in which the temperature of the two streams is not equal, and the temperature difference is strong enough such that the density contrast associated with it is going to induce a large difference in terms of how mixing proceeds between the two streams. So first of all, why are we interested in river confluences? For a wide range of reasons. They basically regulate the movement of sediment and break the river systems. There is lots of interest how the input of nutrients and food is basically transported downstream of the confluence. And of course, one of the main reasons is thermal mixing and thermal pollution. And in fact, all the examples I'm going to talk about are basically cases in which we are talking about two tributaries with difference in temperature, and we are trying to understand what are the mixing mechanisms which result in the mixing of the two streams downstream of the confluence apex. So one important thing which is important for what I'm going to present next is to point out that mixing at river confluences is strongly three-dimensional. So in many cases, what you see in terms of the mixing at the free surface is not representative of what happens over the whole water column. And also the mixing is to a large degree driven by large-scale coherent structures, and you have some evidence of this. In this case, what you can see here are evidence of vertically oriented large-scale vortices. But there are also other type of vortices which you cannot see from pictures taken from the free surface. There are some streamwise oriented cells which are basically developing in the vicinity of the region where the two streams come into contact, and that region we are going to refer to it as a mixing interface. And also another important thing is that the flow conditions are shallow, and by shallow conditions I mean in this particular case the fact that the dynamics of many of these large-scale vortices is strongly affected by bed friction. So let me basically start by reviewing what are the main physical and flow parameters which affect mixing at river confluences. Obviously, one of the most important parameters is the velocity ratio between the two streams. In other researchers are using the momentum ratio, it's pretty much the same thing. Then the angles between the two incoming tributaries and the downstream channel is also important. And most of my talk is going to be about the third effect, which is the density difference associated with the difference in the temperature, salinity, load of suspended sediment, even though, as I already mentioned, in all my examples, we are going to talk about density contrast induced by temperature differences. And then two other factors which are quite important, but I'm not going to discuss in this talk, are the curvature of the downstream channel and the degree of concordance of the bed. In many cases, when a small tributary joins a large river, the flow depth in the tributary is much smaller than the flow depth in the main stream, and this also induces generation of large-scale turbulence and modifies the mixing. Now, in terms of the main types of coherent structure which we generally observe at the river confluence, we basically have, in the case in which density effects are not very important, we typically have two types of coherent structures. So one are the vertically oriented vortices, and even here we have to make the distinctions about two main cases. Maybe the most classical and most often encountered case is the case in which the velocity ratio between the two streams is relatively large, and as a result of this large velocity difference, you have a mean shear acting at the density, at the interface between the two streams. And as a result of that, you are going to generate co-rotating vortices inside of the mixing interface. This is what we are going to be referring to as a mixing, as an interface in the Kelvin-Hepworth mode, and this really corresponds to a shallow mixing layer. Okay? But there is another important case, and this is the case in which the mean velocities in the two tributaries are relatively close to each other. And in this case, what you are going to observe inside of the mixing interface is the formation of counter-rotating vortices, very similar to the vortices you get in the wave path of a black body, like a cylinder, when you have the von Karman vortex. And the mechanism for the formation of this counter-rotating vortices is also very similar. You have two separate shear layers for the two sides of the confluence apex, and as they are interacting with each other, they are basically shedding those counter-rotating vortices, which are still vertical. And then there is another type of coherent structures which you generally do not see from the free surface, but they are also playing a very, very important role in both mixing and in sediment transport. They are, in fact, the main reason for the formation of the confluence caurup. And they are basically referred to as SOV cells, or streamwise-oriented vortical cells, and they typically form in the vicinity of the mixing interface, either on one side or on both sides. And basically they are streamwise oriented, and they are basically like helicoidal vortices, which are not the same thing as the cells of secondary flow, which can also be present at confluences, which are associated with the band curvature and with topographic steering. So I'm going to basically start this talk by a question which I was asked when I was visiting with Jim Best in University of Illinois something like 15 years ago, when he basically asked me if I have any explanation why at some very large river confluences the two streams seem to basically flow together without mixing for a very large distance. And there is a very example case. This is the confluence between the Solimoes and the Negro rivers in the Amazon. And basically this is a huge confluence. And I'm going to show you on the next picture that very close to the confluence apex there is no evidence of mixing at the free surface. But basically what is important to notice here, or to basically be aware of, is that the Solimoes rivers is very rich in suspended sediment. This is why it has that brownish color, while the Negro river contains low sediment but high organic matter, and it has this blackish color. And the two streams have a difference in temperature of about 4 degrees Celsius, besides the differences in the suspended load. And it was observed that the two rivers run side by side for 6 kilometers before they start mixing, at least based on pictures taken at the free surface. So in fact, this is a picture taken close to the confluence apex, and this distance is about 1.5 kilometers. So clearly there is no evidence of those Kelvin-Helmholtz vortices or any other vertical vortices forming near the interface. Okay? Of course, as we go downstream, and here we are already at 20-30 kilometers, you start seeing those kind of billows, which are basically present at the free surface, and even more downstream, you can see already evidence of the things that the mixing patterns are not uniform over the flow length. And I'm going to talk more about this later on. So in order to kind of get a feeling whether or not stratification can have something to do with this phenomena, we are going to consider a small confluence in Illinois, and this is a confluence between the Kaskaskia River and Copper's Flow. There are two very, very small streams. The average flow depth is about 30 centimeters, and the average width is something like 5-8 meters. And this is a confluence which was studied over 30 years or so by the group in University of Illinois led by Bruce Rhodes. So basically I'm going to present you a couple of simulations in a bathymetry which has, in a confluence which has this bathymetry. This is basically the confluence caurup hole here. There is a deposition bar forming at the left bank of the confluence. And I'm going to basically show some results of simulations which capture the dynamics of those large-scale turbulent eddies, but I'm going to basically focus mostly on the time average results. Okay? So I'm going to first do a simulation in which there is a large velocity ratio between the two tributaries. So the left tributary has a velocity which is about 5 times larger than this one. And in the first simulation, I'm going to have the two streams with different temperatures, but there is going to be no coupling with the momentum equation. So basically the temperature will be just a passive scalar which doesn't do anything to the velocity field. And here we are looking at what happens at the free surface. And you can see that we are observing the formation of the Kelvin-Helmholtz billows starting at about 25 times the average flow depth in the mean channel. Okay? And this is basically for a case in which the Richardson number, or correspondingly the densitometric flow number, which is defined with the mean velocity in the mainstream and with the density difference between the two streams, it's equal to 0 in this case. So now if we redo the same simulation, and the only thing which we are going to change is that we are basically coupling the temperature solver with the momentum solver via the Boussinesq approximation. You are going to, and we are again looking at the free surface, you are going to see here that you still observe the formation of Kelvin-Helmholtz vortices eventually, but this formation is going to be delayed such that you go from 25 flow depths to something like 65 flow depths at the free surface. Okay, so this is something which can potentially explain what is seen in the confluence between the solid moist and the Negro River. By the way, the difference of 40 H or 65 flow depths for the solid moist river, it's about 6 kilometers. But that's another story, okay? But certainly, basically, stratification can delay formation of Kelvin-Helmholtz pillows, at least based on what you see at the free surface. And then there is another very important difference, and this is the formation of this elongated region containing mixed fluid, okay, which basically forms near the free surface. And in order to understand how such a region can form, we have to look at the temperature distribution over the whole cross-section. So I'm going to look in the next slide at what happens, how the mean temperature, not the instantaneous one, the mean temperature is distributed in the section S2. So let's start with the case in which density effects is neglected, so there is no stratification. And you can see that here the region containing of the mixed fluid corresponds really to the mixed interface, but there is a little bit of intrusion which basically ejects some of this mixed fluid toward one of the banks, and this intrusion is basically driven by topographic steering and the secondary cells associated with it. And then let's contrast this with what happens in the case in which we have density stratification, where it's true that near the free surface it appears that you have very low mixing across what appears to be the deformed mixing interface, but then you have this region containing pretty much unmixed and denser fluid, and this is surrounded by a region which is relatively large containing mixed fluid. So if you look at the total amount of mixing in this cross-section, I wouldn't say that the case with density stratification has less mixing compared to the case with no density stratification, is that most of the mixing occurs below the free surface, and you cannot see it if you are just looking at the free surface. And then in terms of fluid mechanics, if you want to basically characterize what happens here, you basically start with basically a region which you have dense fluid on one side of the confluence apex and lighter fluid on the other side. And as you basically go away from the confluence apex, you can see the formation of what we are calling a bottom propagating graphic current, which basically first evolves on the downslope and then basically moves on the upslope, but it's a graphic current which basically develops in space rather than in time. And in order to understand how this elongated streak of mixed fluid is forming, well, this just corresponds to when the head of this graphic current is going to go up and up more, and when basically it reaches that very shallow region, it's going to pop up. And by the way, in the solid-moist Negro River confluence, this is the same thing which is happening. So now, the next question which we are going to ask is the development of this kind of intrusion, a general characteristic of mixing between two streams of unequal temperatures. And I'm going to go back to the same Constantinescu river confluence, and we are going to look at a case in which the temperature difference is of 7 degrees Celsius, which corresponds to a densimetric Froude number of 1.6, which is considered to be a case with very strong stratification. Okay, and I'm going to basically show results of 3 simulations. I'm going to start with the simulation in the middle, where we are showing the temperature distribution, or rather the density distribution near the free surface and near the bottom. And here what you can see is that if Constantinescu river is the one which has lower temperature, you can see that you start with blue on one side, and as you go downstream, the blue remains on the same side, while on the copper slope you start with the red. Okay, let's say this is the warmer fluid, and you basically are left with red until the exit. And most of the mixing basically happens in between, inside of the mixing interface. The only difference between the free surface and the bed is that near the bed you have a wider region, and this is because of those SOP cells which are basically also contributing to mixing near the bed. So now let's contrast this with what happens in the bottom picture, and this is what we call case number 6, where in this case Kr basically contains the lighter fluid, and you can see that near the free surface the lighter fluid, more or less because of its inertia, basically goes straight, and you end up with a mixed lighter fluid on the left stream, even though originally the confluence was contained the lighter fluid at the right side of the channel. What happens on in the tributary which contains the denser fluid? Well, here you can see this denser or mixed fluid until it reaches the mixing interface, and then based on what you see at the free surface, it kind of disappears. In reality, it doesn't disappear, it just plunges downwards and it continues near the bed, and most of the mixing occurs when it basically starts interacting with the right bank. There is lots of mixing, and then that fluid gets to the free surface, and then this explains the formation of this region of containing mixed fluid. So you see, you're starting with the light fluid on the right, and the dense fluid on the left, and you are ending up with the light fluid on the left and the heavier fluid on the right. And this is something which can happen only because of stratification effects, as basically the one stream plunges down and moves beneath the other stream. So with this, basically, let me go to the conclusions, because obviously I think I already used all my time. So the main conclusion here is that the main mechanism for mixing, which is basically present in cases with negligible temperature differences, or in more general density difference between the two incoming streams, can be very different from the main mixing mechanisms which are present when stratification effects are important, and typically that happens when the decimetric full number is smaller than 10. And in general, something which I didn't discuss quantitatively in my talk is that the effect of stratification in most cases is to basically enhance the overall mixing in the confluence and not to basically decrease it, even though based on what you see at the free surface, you may think that the main effect of stratification is to decrease mixing. Okay, thank you very much.